Hello there, young students of chemistry. This is a recording regarding the periodic trends. So the word periodic has a specific meaning. If you think of those things in your life that are periodicals, we're talking about newspapers and magazines, things that we can predict when they are coming. So if something is periodic, it is predictable. So there are 4 periodic trends that you will need to know. With these trends, you should be able to look at a periodic table and predict which element has the highest ionization energy, for example. But more importantly, I'd like you to be able to tell me why a particular atom might have a higher ionization energy than another. And that is not because of really its position on the periodic table, but the reason the trends occur to begin with, which has to do with the layout of the periodic table. And really, as everything in chemistry, it's really about attractive and repulsive forces. So we're going to start by just looking at what these periodic trends are actually measuring, because you can't understand why the trend occurs if you don't understand what we're measuring here. You do have a note page to go with this. We're going to probably be skipping around that a little bit, so hopefully you'll be okay with that. So the first of your 4 periodic trends is atomic radius. And just like the radius of a circle measures the size of the circle, if we envision an atom as a circle or a sphere, the radius is telling us about the size of the atom. Please remember that the size of the atom is determined by the electron cloud, whereas the weight of the atom is determined by the nucleus. So the nucleus is where all the weight is. The size of the atom is determined by the electron cloud. So the second periodic trend is ionization energy. And just like the name says, the energy for ionization. And we know that ionization is the removal or attraction of electrons. In this particular case, ionization energy is the energy needed to remove an electron. So we're talking about removal only. And electron affinity. You know that if you have an affinity for something, I have an affinity for coffee. That means it's something that I really like. It's something that I want around me at all times. That is coffee. And electron affinity is just that. You know, it's really a nucleus. A nucleus is attraction for electrons. Like, how much does that atom want to pull electrons toward itself? And then electronegativity is really kind of measuring the same thing, except electronegativity is talking specifically about two atoms that are bonded, and they are sharing a pair of electrons. And it's talking about, okay, which way do the electrons shift? Do they shift toward one atom or another? And that's what electronegativity is. We're going to hit more of that later. So for right now, just know that electron affinity and electronegativity are attraction to electrons. Okay, so these are the things that cause the periodic trends. If we think about the nuclear charge, we know that in the nucleus of the atom, the nucleus has protons and neutrons are just there for mass, but protons are positively charged. We know that the more protons there are, the more attracted they will be to electrons. If you think about, you know, this is going to sound terrible, but I always think about a bar, because like if you own a bar, you want to make the women that are coming to the bar happy, because men don't come into a bar unless there's women in there. And if the women aren't comfortable coming, the men won't come. I guess I watch a lot of Bar Rescue. That might be my problem. So the effect of nuclear charge is just that. Like, the more protons there are, the more attracted they are to the electrons in the electron cloud. And then shielding effect. Maybe, I think I've got something here. Hold on. Right. So effective nuclear charge is determined by the number of protons. And of course, it makes sense that the more protons there are, the stronger those protons will pull on their electrons. Shielding effect is kind of like when you go to a concert and you've got rows of seats, right? The performers way down on the stage or up on the stage. The seats are in rows. You can kind of think of those sections as energy levels. And the farther and farther back you go, the farther you are from the performer. So if you think about that in terms of energy levels of electrons in an atom, you know, electrons that are in energy level 7 are farther away from the nucleus than the ones that are at energy level 1. So we're talking like row 1 versus like, row 1Z or something like that. But the thing that also happens is that the more electrons that are in front of you, they kind of block the effect of the nucleus on the atom. So it's like if you're in a concert and you're in the 7th row, but there's a bunch of people sitting in front of you with great big heads, and you can't see around their heads. So you're being blocked by the performer. So when you have electrons in the outermost energy levels, they're being blocked by the effect of the nucleus by all of the electrons that are coming before them. So you've got all these electrons at energy level 1 and 2 and 3 and 4 blocking those outer electrons from being attracted to the nucleus. So the greater the energy levels, the more shielding effect there is. Those electrons closer to the nucleus are blocking the effect of the nucleus on the electrons farther away. Now, and the farther an electron gets away from its nucleus, of course, the less attraction it's going to have. We spoke about this the other day regarding electrons and attraction when they are farther away from their nucleus, just, like a long-distance love relationship. Farther away you are, the harder it is to stay attracted. So the greater the distance, of course, the less attraction there is. So electrons in an atom that are at energy level 7, they are less attracted to their nucleus than the electrons that are energy level 2. So if you look at a periodic table and you look at maybe magnesium versus calcium, calcium's electrons or outer electrons are at a higher energy level and than magnesium's are. So magnesium is naturally more attracted to its electrons because its outer electrons are closer than the outer electrons of calcium. So there's the basics whys. Now let's talk about the individual trends. So what I was saying here was, if you're looking at magnesium and calcium, remember that magnesium's outer electrons are at energy level 3, whereas calcium's are at 4. So calcium is not only a bigger atom, its electron cloud is bigger at energy level 4, right? But calcium's nucleus is also less attracted to its outer electrons, which causes those other trends. So let's start with atomic size, because I think that's the easiest one to conceptualize, atomic radius. And if we look at this, we're talking about the size of the atom. If we look about the periodic trends across a period, let's go back to that periodic table. So if we look across period 3, all of the outer electrons, sodium and magnesium and aluminum and silicon and argon, all of these outer electrons end in the electron configuration 3 something. So right, these would be 3s2, these would be 3p6, and because they both end in 3, the atom isn't really getting any bigger because of its electron cloud. The electron cloud is still at energy level 3. So what happens here is that the electron cloud actually gets a little bit smaller. And if we look at what's happening on the periodic table as we go across, the 11, 12, 13, 14, 15, and so on, the nucleus is getting bigger and bigger. And since the electrons are at the same distance, they're all at energy level 3, the outer electrons, that is, right? But the nucleus is getting stronger. What happens is that nucleus pulls its electrons in just a little bit tighter, so that as you go across the periodic table, the size of the atom decreases. It gets, listen people, it gets slightly smaller. Not a lot smaller, but slightly smaller. But if we look at a family trend, as we go down the periodic table, radium has outer electrons at energy level 7, whereas beryllium only has outer electrons at energy level 2. Energy level 2 is a lot closer to its nucleus than electrons at energy level 7. So radium, is much larger than beryllium is. Now, when I say much larger, we're still talking about like picometers, 10 to the negative 12 meters. A number is still really close to 0. But radium as an atom is a bigger atom than strontium or beryllium. So as we go down, the size of the atom increases because there are more electrons. The outer electrons of those elements at the bottom of the family are at higher energy levels than the outer electrons of the elements at the top of the family. Okay, make sure you get the Y's. So the periodic trend for atomic size is that as you go across a period, the atomic size decreases because the electrons are at the same energy level, but the number of protons in the nucleus gets greater, which causes the electrons to be more attracted to the nucleus. Slightly smaller atom. The size goes, as you go down a family, the size of an atom increases because the elements at the top of the family have outer electrons at lower energy levels than the elements at the bottom of the family. This is the kind of stuff that I'll expect you to explain. So I might say to you on a quiz, I might say, oh, why is chlorine smaller than bromine and sulfur? And then you'd have to explain to me, well, chlorine is smaller than bromine because bromine has outer electrons at the 4th energy level, where chlorine only has them at the 3rd energy level. Chlorine is smaller than sulfur because sulfur and chlorine have electrons at the same energy level, but chlorine's nucleus has a stronger pull on the electrons with 17 protons versus the 16 protons. So that's the kind of questions I'm getting at on things like this. I mean, I am going to ask you some of those easier ones, just like, oh, which one's smaller, fluorine or oxygen? And then you would go fluorine. Which one's smaller, iodine or sulfur? And you would say sulfur. But sometimes I'm really going to want you to explain that and let me know that you understand the why that occurs. Okay, let's go on to the next periodic trend then. We're going to talk about, what was the next one on your list? Ionization energy. Ionization energy is the energy needed to remove an electron. So let's think about this in terms of the size of the atom, the effective nuclear charge, which nucleus has a stronger attraction to the electrons, as well as any shielding effect that might occur. So if we look at it going across a period, we're just going to stick with period 3. If we go across a period, a shielding effect is constant because all of those electrons are at energy level 3. They're all sitting in the same row, right? This is 3s2, 3p6. So shielding is constant. We don't have to worry about that. And the electrons are a little bit closer to the nucleus over here by argon, a little bit closer to the nucleus in argon than they are in magnesium. So magnesium's outer electrons, even though they're at energy level 3, they're a little bit farther away than the outer electrons of argon because argon's nucleus is pulling them in a little bit tighter. And we also know that the effective nuclear charge is increasing. The 18 protons of argon are going to hold the electrons a lot better than the 11 protons of sodium. So with an increased nuclear charge and the electrons are slightly closer to the nucleus, ionization energy as you go across the period increases. The more attracted the nucleus is to the electrons, the harder it is to remove that electron, so the energy needed to remove the electron gets higher and higher and higher. Now let's consider that trend for the family. We'll stick with family 2A, going down. What's happening as we go down the family, we can see that the nucleus is getting bigger. We have 4 electrons, 12 electrons, 20 electrons, 38, 56. But as we go down the electrons, as we go down that family, the outer electrons are getting farther and farther away from their nucleus. So again, radon has outer electrons at family 7 versus the outer electrons for magnesium are at energy level 3. I think I said family 7. I meant to say energy level 7. I'm sorry. So as we go down, radon has outer electrons at energy level 7. Beryllium is only at energy level, has outer electrons at energy level 2. So as the electrons get farther and farther away from their nucleus, it really doesn't matter that the nucleus is getting bigger, because the farther away the electrons get, remember, increased distance is decreased attraction. So the outer electrons of radium are not very attracted to radium's nucleus, whereas the outer electrons of magnesium are more attracted to magnesium's nucleus. So it is much easier to take an electron away from radium than it is from magnesium. So as we go down a family, ionization energy decreases. The effective nuclear charge increases as we go down the family, but that really is overcome by this extraordinary distance in the electron cloud. The electron cloud at energy level 7 is just really far away from its nucleus, and those electrons just aren't so attracted to its nucleus anymore. Okay, so we've covered 2 of the trends, atomic size and electron ionization energy. Electron affinity and electronegativity are going to have the same trend because they're really kind of measuring the same thing, attraction to electrons. And the trend is going to be caused for the same reasons. So let's think about nuclear charge. Let's think about shielding. Let's think about how far the electrons in the atoms are away from their nucleus. So again, we'll look at period 3 and family 2A. As we go across the period, we know that nuclear charge is increasing. So we know that argon has more attraction to its outer electrons than sodium has to it. And that is because argon has a greater nuclear charge with 18 protons. That's going to pull its electrons, it's going to hold its electrons tighter than the 11 protons of sodium will. So as we go across, the atom gets slightly smaller, the effective nuclear charge increases. So what does that mean about the ability to attract electrons? The distance from the nucleus, by the way, we know doesn't change. These are still 3s, 3p, right? Those outer electrons are 3s, 3p. But what does this mean then about the ability to attract electrons? Now we have to kind of leave argon out of this one. Argon is a noble gas, and it cannot attract electrons. And if we remember why, with the S being full and the P being full, argon's electron configuration is neon, 3s2. Let's write this properly. I'm sorry. Argon, 3s2, 3p6. Its outer electrons, its outer shells are full. P has 6 electrons in it and S has 2. Those are full. That makes 8 valence electrons. That is very stable. So outside of argon, as you go across the periodic table, we're getting a greater effective nuclear charge, which causes the electron affinity to increase. the electron affinity increases because the nuclear charge increases. There's 17 protons in chlorine versus 11 protons in sodium. The things that are not changing are the electron's distance from the nucleus. I mean, it changes slightly if you consider size. It gets slightly smaller. And the other thing that's really not changing is shielding effect. If we go down family 2A, we have electrons at energy levels 1, 2, 3, 4, 5, 6, and 7. So the outer electrons of, let's say, barium are at energy level 6. The outer electrons of calcium are at energy level 2. So those electrons that are already there, so barium has 56 electrons. If it's going to attract any more electrons, they're going to come in at the 6th energy level. And the electrons that are already there are really losing their attraction for the nucleus. You know, one time I went to a concert at that pavilion there on over there by the Starlight Theater. The people that were on the lawn, they were just wandering around. They weren't even looking at the performer on the stage. They were so far away that it had no effect on them at all. They were just there to be with their buddies. So it's the same thing with electrons. The farther away the electrons are from the nucleus, the less attracted they are. And that really is why electron affinity, as you go down a family, decreases. Right? Barium has less electron affinity than calcium does because the electrons that would join barium would join it at energy level 6, and that's just too far away for them to be interested in doing that. So because the electron cloud gets bigger and bigger and bigger, we have less electron affinity for those elements at the bottom of the periodic table than we do at the top of the periodic table. I will say this too, the more electrons you get in the electron cloud, electrons are all negatively charged, so they're going to naturally repel each other. They just repel, 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 and the more electrons you add, the more repulsion there is. So there's another reason that those elements that are at the bottom of the periodic table in these families here would not want to attract more electrons. So what you should be able to do is to look at a periodic table with some elements and determine which element has the greater or least of any of those values. Like, you know, I might say, oh, which atom has the greatest electronegativity of these three? Or I might say, which atom has the least electronegativity of these three? For example, if we have aluminum, silicon, arsenic, I might say, oh, which one of these atoms is biggest? And you would say arsenic. Why is arsenic bigger? Arsenic's outer electrons are at energy level 4 versus silicon and aluminum, which are at energy level 3. So arsenic is bigger than silicon or aluminum. So then you might want to put those in order. Okay, well, which one of those is small? Which one is the next biggest? Is it aluminum or silicon? And you would choose aluminum. Because we know as you go across a period on the periodic table, silicon and aluminum both have outer electrons in the 3p, but silicon has 14 electrons, which is going to pull its electrons a little bit closer to the nucleus than the 13 protons of aluminum, so aluminum is slightly bigger. So aluminum is bigger, arsenic is bigger than aluminum, which is bigger than silicon. And I would expect you to do that for all of the other trends as well. Like which one Which of these three elements has the greatest electronegativity? So if the question's asking for the greatest electronegativity, right? Electronegativity is abbreviated capital E sub N. So electronegativity, we know that as you go down a family, electronegativity decreases. As you go across a group, electronegativity increases. So we know that carbon is going to have the greatest electronegativity. So carbon is greater than beryllium and magnesium. And then if we consider beryllium and magnesium, the one that is higher is beryllium. Electrons would be joining that at energy level 2, whereas magnesium electrons would be joining that at energy level 3. So because the electrons are already farther from the nucleus of magnesium than beryllium, magnesium will not attract electrons as well as beryllium does. Carbon attracts the most because it has 6 protons, and those 6 protons are at the second energy level, so it's a really nice strong attraction there. By the way, the element that has the greatest attraction for electrons ever is fluorine. Fluorine is a wickedly high electronegativity. Okay, this has gone on 26 minutes. What I would like you to do is answer those questions that are on your problem set. Start working on that. Some of them I'm just asking you to tell me, hey, which one is bigger? Which one is smaller? Some of them I want you to explain why you are making those choices. And the explanation is going to have to do with effective nuclear charge, electron distance from the nucleus. You may not say fluorine is smaller than oxygen because fluorine is to the right of oxygen on the periodic table. That, my friends, is not a reason. You need to explain it using attraction and repulsion, effective nuclear charge, electron distance from the nucleus, in terms of outer electrons and electron configuration, as well as shielding effect. Okay, thank you.